The universe is a wonderful place full of unanswered questions. However, there are questions that we are able to answer. This documentary will show the life cycle of a star going from its gas cloud to its final state, rebirth. We will also be discussing the Hertzsprung-Russell diagram. This is the life cycle of a star. The star's life begins in the gas cloud, otherwise known as a nebula or stellar nursery. This is a giant cloud of dust and gas. They form over millions of years due to the very small gravitational forces of attraction between the particles of dust and gas pulling them together, thus eventually resulting in vast clouds of dust and gas. In the coldest and the densest regions of the interstellar medium, we find clouds whose cores contain molecular gases, this being primary molecular hydrogen gas. The molecular clouds usually have a temperature of only about 10 Kelvin, and the high concentration of dust grains protect the molecular gases at the center of incoming photons. If the gas cloud is not quite cold or dense enough for hydrogen molecules to survive, we end up with a cloud of neutral hydrogen atoms. These clouds tend to have temperatures of around 100 Kelvin and are commonly named H1 clouds, since astronomers often refer to neutral hydrogen as H1. Occasionally gas clouds are found close to a very hot star, which heats the gas to about 10,000 Kelvin. The radiation from the star ionizes the hydrogen, which later emits light as it recaptures an electron and returns to its lowest energy state. These gas clouds result in one of the most common forms of emission nebulae and are usually referred to as H2 regions. As time passes, tiny variations in the nebula cause denser regions to begin to form. These regions pull in more dust and gas, increasing the mass and density as the gas cloud becomes hotter and hotter. Gravitational energy is converted to thermal energy, and in one part of the cloud the protostar forms. It has begun its journey in becoming a star. Unfortunately, as objects are shrouded in dust and gas, it is impossible to see them from Earth-based observatories. They can, however, be seen using infrared technology, which peers through the veil of dust that surrounds them. In the core of a protostar, extreme pressure and temperatures are needed in order to overcome the electrostatic repulsion between hydrogen nuclei in order to fuse them. As the protostar grows in mass, it grows larger and hotter, and there is enough kinetic energy to fuse hydrogen into helium. Nuclear fusion begins, and a star is born. As collapse continues, a disk of gas forms around the protostar, and jets blast out from the top and bottom of the star. This produces spectacular shock waves in the clouds. Eventually, temperatures and pressures in the protostar are sufficient that it can ignite nuclear fusion, converting hydrogen atoms into helium. When this process gets going, a star is said to be in the main sequence phase of its life. During the main sequence, gravitational forces act to compress the star, but the radiation pressure from the photons emitted by fusion and the gas pressure from the nuclei in the core push outwards and counterbalance it. The star maintains equilibrium and is in a stable state. In a star similar to our Sun, which is in its main sequence, the core accounts for roughly 20% of its radius and is in the region where all the energy of the star is released. This energy must then travel through a radiated zone where photons are absorbed and re-emitted. Energy proceeds to travel through a convective zone where columns of hot plasma transport bubbles of heated gas to the surface of the star where it's released. The material cools and falls back down into the star where it's heated up once again. The journey for a single photon to travel from the core out to the surface can take over 100,000 years. The main sequence phase can last a long time. Our Sun has already been in this phase for 4.5 billion years and is estimated to last another 7.5 billion years before it runs out of nuclear fuel. A way of representing the life cycle of a star is using the Hertzsprung-Russell diagram. This diagram is a graph of stars in our galaxy, which shows the relationship between luminosity and average surface temperature. Luminosity is the total radiant power output of a star. Our Sun has a luminosity of 3.85 times 10 to the power of 26 watts. And luminosity is often plotted in units relative to the Sun, with one solar luminosity equaling the luminosity of the Sun. Unusually, the x-axis shows temperature increasing from right to left. Most stars, like our own Sun, are found in a diagonal strip and are in their main sequence. Main sequence stars vary greatly in temperature, but generally the hotter they are, the more luminous. This is why they appear in a diagonal strip from top left to bottom right. When smaller stars evolve into red giants, they branch off the main sequence in a line, as seen on the diagram. White dwarfs, the next stage after red giants, are found along a separate line at the bottom left corner, showing they are hot but dim. Larger stars evolve into red supergiants, which are bright but relatively cold and are found around the top right of the graph. The core of stars with low mass are cooler than those of more mass, and so remain on their main sequence longer. Eventually, a star will run low on hydrogen fuel in their core for fusion, and the next stage in its life begins. The mass of our Sun, 1.99 times 10 to the power of 30 kilograms, is often taken as a base unit, and is known as its solar mass. If a star has a mass between 0.5 and 10 solar masses, it will evolve into a red giant. At the beginning of this phase, the gravitational forces are greater than the gas and radiation pressure, as less energy is produced by fusion. The core of the star collapses in on itself and shrinks, causing pressure to increase enough to start fusion in a shell surrounding the core. The core of a red giant is inert, and fusion no longer takes place as very little hydrogen is left, and that temperature is too low to provide the kinetic energy needed for helium nuclei to overcome the electrostatic repulsion between them and fuse. In the surrounding shell, hydrogen continues to fuse into helium, and the star expands as layers move away from the core. These layers cool as they expand, which is what makes the star appear red. The energy from the fusion of helium causes the star to expand to many times its original size. As the energy is distributed over such a large area, the surface temperatures are relatively cooler, becoming only around half as hot as the Sun. After a star has become a red giant, the outer layers around the core expand and drift off into space as a planetary nebula. It may collapse again to form another star, or even a new solar system with its own planets, which explains the name. A planetary nebula is an object consisting of a glowing shell of gas and plasma. They are actually unrelated to planets. The name originates from a supposed resemblance to giant planets. They are a relatively short-lived phenomenon and last only tens of thousands of years, as opposed to the typical solar lifetime of several billion years. Only about 1,500 are known to exist in the Milky Way. Planetary nebulae are important as they play a crucial role in the chemical evolution of the galaxy, returning material which has been enriched in heavy elements back into interstellar space. Also, in other galaxies, planetary nebulae may be the only objects observable enough to give information about chemical abundances. Once a small star has neared the end of its life, it evolves into a white dwarf. This happens when red giants blow off the material of their outer layers, creating a planetary nebula that drifts off into space. What is left behind is a hot core, the white dwarf. This core is incredibly dense, crushed due to immense gravity, and is extremely hot. A white dwarf is often similar in size to the Earth, but have a mass similar to our Sun, which is why they are so dense. Fusion does not take place inside, the star is dead. An important rule of quantum physics, the Pauli exclusion principle, states that two electrons cannot exist in the same energy state. This means as the core collapses under gravity, electrons are squeezed together, and this creates a pressure that prevents further collapse. This pressure generated by the electrons is known as the electron degeneracy pressure. However, this pressure is only sufficient to prevent gravitational collapse if the mass of a core is less than 1.44 solar masses, the Chandrasekhar limit. This is the maximum mass of a stable white dwarf star, and if the mass exceeds this limit, the star will not be stable and will continue to evolve. Over time, a white dwarf radiates its energy and cools. Over a long time, it will begin to crystallize. The low temperature of the star means it no longer emits any significant heat or light, and once it is fully cooled, it will become a cold black dwarf. The star will have reached the end of its life. The length of time needed for the creation of a black dwarf is calculated to be greater than the age of the universe, and it is believed that no black dwarfs currently exist. Main sequence stars with masses greater than 10 solar masses do not evolve into red giants, as the cores are of a much higher mass, so they are much hotter and consume all their hydrogen fuel much faster than smaller stars. Like red giants, the core starts to collapse under gravitational forces, but as the core is much hotter, fusion of helium nuclei into heavy elements occurs. These larger stars evolve into red supergiants. The star's core causes it to expand, and temperatures and pressures provide the necessary energy to fuse massive nuclei together, allowing a series of shells to be formed within the star. This process continues until an iron core is created. Iron nuclei cannot fuse as the fusion will not produce any energy. The star becomes heavily unstable and the layers implode and reflect off the solid core, ejecting all the core material into space as a Type II supernova. This image shows the different elements created by fusion in the core of a red supergiant. The central iron core is made of a stable iron nuclei and cannot fuse any further. Red supergiants can have masses ranging from 10 to 70 solar masses and can have brightnesses from 30,000 up to hundreds of thousands times the solar luminosity. They are found in less elliptical galaxies, globular clusters, and spiral galaxy bulges, which are believed to be made up of old stars.
The supernova is the explosion that occurs towards the final stages of a large star's life cycle, and is the biggest explosion that can be found in space. They can occur in one of two ways, both of which involve changes in the star's core. The first way is associated with binary star systems, where two stars orbit the same point and are known as Type 1 supernovae. One of the two stars is a carbon-oxygen white dwarf, which takes nuclear fuel from the other star in its system. Eventually, the white dwarf has too much matter, its mass exceeds the Chandrasekhar limit, it becomes too hot and it explodes. The second way in which a supernova can be created is when a single star uses up its nuclear fuel, causing mass of the star to flow into the core. This is called a Type 2 supernova. Similarly to those in the binary system, the star's core takes on too much mass and cannot withstand its own gravitational force, causing free electrons to be compressed within the spinning core as it subsequently collapses on itself. When exploding, the energy emitted by the explosion outshines the entire galaxy the supernova is in. These explosions are responsible for the creation of heavy metals like iron. The shockwaves produced by the explosion can lead to the compression of gas clouds and subsequently the formation of new stars. The creation of supernovae also results in different outcomes for the future of the star. A supernova explosion blows the outer layers of the star away into space while the core remains. However, as the core no longer produces nuclear fusion, the outward pressure originally generated is lost, and the crushing force of gravity begins to condense and collapse the core itself, creating a neutron star. Neutron stars only form if the mass of the core is greater than the Chandrasekhar limit, and the electron degeneracy pressure cannot prevent gravitational collapse. Although relatively small, with diameters of about 20 kilometers, neutron stars are incredibly dense, as they have almost 1.5 times the mass of our Sun. They are so dense, in fact, that even a sugar cube-sized neutron star would weigh around 100 million tons on Earth. This incredibly high density causes protons and electrons to combine to form neutrons, hence the name of these stars. We do not know the compositions of their cores. It could consist of a neutron superfluid or possibly an unknown state of matter. Many neutron stars belong to a subclass called pulsars. Pulsars rotate extremely rapidly, creating magnetic fields trillions of times stronger than the Earth's, and beam radio waves that can be periodically detected across Earth. Less than 2,000 pulsars have been found, though there are predicted about 1 billion neutron stars in just our galaxy. Following a supernova, if the core of a star has a mass greater than 3 solar masses, it does not become a neutron star. The gravitational collapse continues to compress the core, resulting in a magnetic field so incredibly strong that an object would need an escape velocity greater than the speed of light in order to escape. The star has become a black hole and nothing can escape. It is believed that extremely large black holes with masses of several million solar masses are at the center of most galaxies. Although most black holes themselves cannot be seen, as the massive gravitational forces mean even light cannot escape, it is possible to observe the effect of a black hole on the matter around it. Gas, dust, and other stars close to a black hole can be sucked in by gravity, and as material swirls around the black hole, it collides with the material, producing heat and light. As this happens away from the black hole, the light produced can escape, and we can see this activity. Many strange things are associated with black holes. Time dilation is a phenomenon that occurs due to the extreme gravity of a black hole. An object within the black hole's gravitational field experiences the slowing down of time relative to observers outside the field. From the perspective of a distant observer, an object falling into a black hole seems to slow down and fade. It never quite reaches the event horizon. When it finally does, the object is so dim it cannot be seen anymore. Quasars are objects powered by black holes that are 1 billion times larger than our Sun. They shine so bright that they eclipse the galaxies that contain them, and have fascinated astronomers for decades. They only exist in galaxies with supermassive black holes, where particles of gas and dust are accelerated away from the black hole at near the speed of light. The particles stream in jets above and below it, with a central ring of gas and dust forming. Quasars emit vast amounts of energy. They are among the brightest objects in the entire universe and can shine 100,000 times brighter than the Milky Way. The expanding shells expelled in planetary nebulae and the material exploded by supernovae will both eventually drift from their place of origin and merge with the gas and cosmic dust that floats in space between stars. The gas and debris from a supernova remnant may drift into a stellar nursery where it would mix with material and begin the process of forming new stars. It provides new stars with the heavy elements that are produced during the supernova stage, and leftover material may coalesce into the star's family of planets. If the debris does not drift into a stellar nursery, at some point the gravity of the passing star or the shockwave from a nearby supernova may cause it to contract, which begins the life cycle of the star all over again. This process repeats endlessly throughout the universe, and it is this process which creates all the heavy elements needed for life. Our solar system formed from a second or third generation nebula, leaving a great amount of heavy elements on Earth. Every atom in every body on Earth comes from stars, either from the nuclear furnace of a star or from the fiery explosion of a supernova. And life on Earth, like with stars, repeats that cycle of life, death, and rebirth.